Section 3.1, this is our introduction to exponential functions. I need to move my computer back. All right, so problem number 1 is a guided example where a word problem example where we can see where we might encounter exponential functions. And we're also gonna talk about the way that exponential functions grow, okay? Your recently deceased great uncle left you some money in his will, but you have to make a decision. You have 2 options for how to receive your allotment. Option A, you can get $1,000 deposited on December 31st in a bank account with your name on it, and each day an additional $1,000 will be deposited until January 31st. So you start with $1,000, and then every day you get another $1,000 for the entire month of January. Not too bad. Option B, you start off with a penny. Okay, 1 penny. That's going to be deposited on December 31st. And each day the amount is doubled until January 31st. All right. So before we calculate anything, you have to decide, and I'm going to ask you guys to share with me in the chat. There's not necessarily a wrong answer, but which option would you choose? Would you want $1,000 deposited each day? Or so $1,000 and then an additional $1,000 every day, or 1 penny and then the amount is doubled every day. And this is just for the month of January. So think about it for 5 seconds and then tell me which option you would like. Share with me in the chat. I'll tell you which one I'll choose to after you guys share. All you have to do is say A or B, option A or option B. Okay, we're getting overwhelmingly some A's, right? Start with $1,000 and keep on giving me $1,000 until the end of the month. Life sounds great. I would love somebody to give me $1,000. But luckily, all of my great uncles are doing well, so I don't have an inheritance coming anytime soon. All right, we have a couple of people who choose B. So Faith and Kurt both chose B. Everyone else pretty much chose A. All right, let's explore. A couple more B's are coming in too. Let's explore which would, okay. So when I said there's no wrong answer, I mean, free money is free money, but obviously one of these options will give us more money than the other. Let's explore how much money we'll have at the end of the month with either option. All right, so which option would give you the most money after 31 days? Some of you said A, some of you said B. Let's look at what happens. So I'm gonna put a note here, put a star, I should say. We do have projects for this class. We haven't had a project yet. There's 2 projects. I'm going to post the first project over the weekend. You'll have like several weeks to complete it. But the first project has a table on it that's similar to this one. So I'm going to put a star by this so you can remember to come back to it when you look at your project. Not the same numbers, but the same kind of setup. All right. So for option A, we start off with $1,000 and then get $1,000 per day. So on December 31st, we have $1,000. By January 1st, 2000, January 2nd, 3,000, and then this is the total amount of money we have. January 3rd, 4,000. We see the pattern here for the first column. We can keep on adding $1,000 for each day. Oops. We're at 6. All right, so by the 10th day, we have $11,000. Then how much money will we end up with on the 31st day? We'll end up with $32,000. $1,000 for all 31 days in January, and then the extra $1,000 that we got on December 31st. We can also set up an equation to model this situation. We'll do that in a second. All right, for option B, now we're starting off with pennies, not even dollars. You start off with 1 single cent, and then on the second day you have 2 cents. And then if we double every day after that, 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32, then 64, then 128, then 256, then 512, then what's next? 1024. Now let's be clear. Again, this is in terms of cents. So that 1,024 is really $10.24. So after 10 days, with option A, you'll end up with $11,000, but with option B, you'll only end up with $10.24. All right, so at this point, it's looking like option A is better, but remember, we have to do this all the way until the end of the month. So in the long run, as I'm sure you guys can guess, you'll be surprised, but doubling will end up giving you way more money. All right, so using the table, for option A, find the average rate of change in the account from day 3 to day 5, and the average rate of change from day 7 to day 10. Does this represent a linear function? And write the linear equation. At this point, we should be able to tell that this represents a linear function. We're changing by the exact same amount every day. How much are we changing by? $1,000. We're told that. So for option A, this is linear. After day 5, if we have the change or the average rate of change for day 5, we have $6,000. Day 3, $4,000. 5 minus 3 is the change in days. That's $2,000 over 2 days, which is $1,000 a day. Okay. Same thing would be true for days 7 to 10. We get $1,000 a day. This is linear because the change is constant. We get the same exact change for each day. So our linear function would be, our slope is $1,000. Also, we start off with $1,000. So B is also 1,000. And if we put this together, let me scroll back up. That's given to us in the table as well. So if we put those two things together, for option A, the linear function, we're calling it A of t. A of t would be 1,000t plus 1,000, where t is the number of days that you've, or after you started the account, I should say. All right. So the first option here, where we add the same amount over and over, $1,000, this represents a linear function. But since this section is called exponential functions, I'm sure you can guess that option B must be exponential. Let's talk about what the difference is and then how we can set these things up. For option B, if we try to find the average rate of change from day 2 to day 4, so after 2 days, or on January 2nd, you have 4 cents, and on January 4th, you have 16 cents. So we're going to use that for the next part down here. The average rate of change from day 2 to day 4 was, what did we say? 16 cents minus 4 cents over 4 minus 2. That's 12 over 2, which is 6 cents per day. Okay. But what about for days 5 to 7? We look back up in our table. We see at day 5, we have 32 cents. And at day 7, 128 cents. All right. So the average rate of change from day 2 to day 7 would be 128 minus 32 over, wait, that's days 5 to 7, sorry. 7 minus 5, okay? 128 minus 32 is 96. And 96 divided by 2 is 48. So that's 48 cents per day. What this is showing is that 48. The average rate of change is not constant. So if we're adding the same amount every day, that's a constant average rate of change. But here we're doubling every day. So the first day, if we look in the table really quickly, the first day we increased by 1 cent. The second day, we increased by 2 cents. On the third day, we increased by 4 cents. So you can see that the change is not constant. Whereas over here, the change was 1,000, 1,000, 1,000. One of the main things that we harped on in chapter 1 was that if the average rate of change is constant, we have a linear function. But if the average rate of change is not constant, it's not linear. So table B does not represent a linear function. So no, because the rate of change is not constant. But what we do have there is an exponential function. It turns out if we double the outputs over and over, then each of those outputs can be written as a power of 2. So that's what we're told in part D. We're asked to write each amount in the table as a power of 2. Let me erase a couple of the extra things we have here. So on day 0, we have 1. That's 2 to the 0 power. On day 1, we get 2. That's 2 to the first power. Day 2 is 4. That's 2 squared. Day 3 is 2 to the third. Day 4, 2 to the fourth. Day 5, 2 to the fifth. So doubling just gets us all of the powers of 2. 2 to the 6th, 2 to the 7th, 2 to the 8th, 2 to the 9th, and 2 to the 10th. So it's not on here, but what if I wanted to know how much money we have at the 22nd day? That would be 2 to the 22nd power. Whatever day we're on, that gives us our exponent in this case. All right. So for part E, it says, from your results in part D, write an equation B of T that represents the amount in the account after, that rhymes, after 2 days. I feel like Dr. Seuss in here. There would be B of T equals 2 to the T cents in the account, where T represents the number of days in the account. All right, any questions about this before we go on to problem 3? So again, what we should take so far is the first column look like the stuff that we've done before. For option A, we get a linear function and we can find the slope and the y-intercept. For the second column, our terms are not linear, so it's not a linear function. We actually end up getting something that looks like 2 to the T power, which will be an exponential function, powers of 2. All right, then part 3, using the equations in 2D and 2E, find the amount in each account after the 21st day and write the answer in dollars. We said A was 1,000 T plus 1,000. So A of 21 would be 1,000 times 21 plus 1,000. We end up with $22,000 in the account. Life still ain't bad. All right, for option B, B of 21, that would be 2 to the 21st power. All right, I don't know what 2 to the 21st power is, so let's put that into our calculators. 2 to the 21st. All right, remember this number is in cents though, not dollars. 2,097,152 cents. We're asked to put our answer in dollars. So to convert from cents to dollars, I'm sorry, I have something in my eye. To convert from cents to dollars, you need to move your decimal place over 2 units to the left or divide by 100. This would give us 2,097,1.52. So $20,971.52. As you can see, at first, option B was much, much less than option A. But now option B is still less, but it's a little bit closer than what we saw before. So option B is catching up. All right, and then for part B, it says use the equations in part D, 1D and 2E, to figure out how much we will have at the end of the month. So after the 31 days in January are up, what do we have? It'll be A of 31 versus B of 31. A of 31 is 1,000 times 31 plus 1,000, which would be $32,000. Makes sense, right? You get $1,000 for each day plus an extra 1,000. B of 31 will be 2 to the 31st power. Let's calculate it. All right, 2 to the 31st power. Oh, that's 2,147,483,648 cents. So that's not in dollars. To convert this to dollars, we need to move over 2 decimal places, remember? So we get 21,474,836.48. Now this brings us back to our first question. Which option would be the better option? Based on our knowledge of what we had before, or just thinking about the numbers, it sounds like if you start off with $1,000 versus starting off with a penny, starting off with $1,000 would be better. But in the long run, doubling your money over and over will end up growing much, much, much larger than just adding $1,000 over and over. Okay, so I mean, I would choose to be a millionaire. I'm already a thousandaire. That's cool, but I would rather be a millionaire. So I would choose option B. And after seeing this, most of you will probably choose option B too. Okay, option B, it gives us the most money. And really the big thing that we want to take from this is, one, when we double something, we get an exponential function, which we're about to define. The average rate of change is not constant for exponential functions, and exponential functions start off really small, but they grow very, very, very big very quickly. And part D, state the practical domain for both functions. In both cases, we are looking at the input being the number of days that the money is in the account, and where the money is in an account until the end of January. January has 31 days. So the practical domain is that 0 is less than or equal to t, which is less than or equal to 31. All right. So like I said, when I post the project, you'll see that there's a problem similar to this where you're given 2 different jobs. One is linear, one is exponential, and you have to see which one is the better job. But moving on, there's more with this problem. It never ends. All right, moving on. Oh no, this is a different problem. Good. As I said, problem 2 is an exponential problem or an exponential function. Here in media example 4, we're asked to compare the graphs and tables of linear functions versus exponential functions. The big difference again is linear functions grow at a constant rate. So same change, as x increases by 1, the y's are increasing at the same rate. That's the slope. Exponential functions do not grow that way. So let's fill in this table where we compare 2 times x versus 2 raised to the x power. 2 times 0 is 0. 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 6. 2 times 4 is 8. 2 times 5 is 10. Okay. So putting that on our graph over here, we have 0, 0, 1, 2. They didn't make this very easy to draw. 1, 2, 2, 4, 3, 6, 4, 8, and 5, 10. Boom. That's a linear function with a slope of 2. All right. For 2 to the x, 2 to the 0 power is 1. 2 to the first power, 2. 2 squared, 4. 2 cubed, 8. 2 to the fourth, 16. And 2 to the fifth, 32. So we start off at 0, 1. and then we have 1, 2. Oh, well, that's the same. 1, 2. And then we have, what's next? 3, 8. I'm sorry, 2, 4. Almost missed one. 2, 4. Oh, look, it's the same again. And then 3, 8, 4, 16, 5, 32. All right, so for our exponential function, it starts off really low, and then it curves upward and starts to increase really, really quickly. So as we can see, exponential functions in the long run are a lot bigger or give us bigger outputs than linear functions. Okay, what do you notice about the outputs in the table and the graph for each function? The outputs for 2x increase by the same amount. 0 to 2 is 2, 2 to 4 is 2, 4 to 6 is 2, 6 to 8, 2, 8 to 10, change of 2. But the outputs for the exponential function 2 to the x are not constant. 1, this is a change of 1, then a change of 2, then a change of 4, then a change of 8. So the rate of change is not constant. All right, finally, we get to our formal definition of an exponential function. 2 to the x is an example of an exponential function. Formally speaking, an exponential growth function is, this is the case when a is equal to 1. So it's of the form f of x equals a times b to the x. A can be any non-zero number. So, 2, 5, 6, 9, 10. And then the exponential part is the b to the x part. B has to be a number that's positive, and b cannot be equal to 1. Okay? If we have a function of this form, I'll give you a couple of examples. Something like f of x equals 5 times 2 to the x. F of x equals 1/2 times 6 to the x. F of x equals 0.25 times 1.35 to the x. These are all examples of exponential functions. The big thing is, for an exponential function, the x is in the exponent, okay? You have a numerical base and a variable exponent, okay? When this a term is positive, we get something that's called an exponential growth, which just means that as we look from left to right, the graph is increasing. What else? And we'll focus a lot today on talking about what the graphs of these types of functions look like. In general, though, they all will have that same kind of shape as 2 to the x. The graph will look something like this. Okay, did I miss anything that's down here? Oh, so this is a growth function. B is called the growth factor. I'm gonna highlight that. So B is called the base and also called the growth factor. And that's all the important stuff that's shared here. A is the initial value, but we'll talk about that a little later. All right, so now that we know what exponential functions look like, we have a number raised to the x power. That makes it an exponential function. In the next section, we're going to practice identifying exponential functions. Is a exponential 2.06 raised to the x power? The answer is yes. This is exponential. It does have a growth factor. The growth factor would be the base b. So we'd say yes, and b, which is the growth factor, is 2.06. Okay. For part B, y equals 3x. This is a linear function, and linear functions do not have a growth factor. Okay. For part C, 0.95 to the x power. This is an exponential function. However, For exponential growth, p has to be bigger than 1. So b does have to be greater than 0 just to be an exponential function. That's how we define exponential functions. But the base has to be greater than 1 in order for it to be a growth. If our base is not greater than 1, we still have an exponential function, but it's called a decay function, which we'll get to later. So this is an exponential function, but it does not have a growth factor. It has something called a decay factor, which we'll talk about later. And I should emphasize here that this is the growth factor. For 3 to the x, again, this is exponential. The base is 3. So that is a growth factor. It's bigger than 1. For y equals 5 over 4 to the x, exponential again. The base this time is 5 over 4. Excuse me, 5 over 4. That is bigger than 1. 5/4 is 1.25. So this would be a growth factor. And the last one, 10 to the x power. This is exponential again. The base here is 10. And since 10 is bigger than 1, the base is a growth factor. All right, so any number raised to the x power or any positive number raised to the x power is an exponential function. If that base is bigger than 1, we call it a growth factor. If it's less than 1, we call it a decay factor. Exponential functions versus linear functions. For linear functions, if we're looking at a table, the outputs change via addition. We add the same number over and over to get to the next output, okay? For exponential functions, the outputs change with multiplication. You multiply by the same number over and over to get to the next output. Example 6 shows a worked out example of this. If we look at 3x plus 4 versus 3 to the x, everything's already filled in here. Looking at the outputs, to go from 4 to 7, we add 3, which is the slope. 7 to 10, add 3. 10 to 13, add 3. 13 to 16, add 3. 16 to 19, add 3. The rate of change is 3, and we add 3 to get to the next output. For an exponential function with a base of 3, we don't add 3 to get to the next output. We multiply by 3. 1 times 3 is 3. 3 times 3 is 9. 9 times 3 is 27. 27 times 3 is 81. 81 times 3 is 243. So when we're looking at a table of data, if we notice that our outputs, to get from one output to the next, we add the same number over and over, the outputs are changing by addition, that's linear. But if the outputs are changing by multiplication, that represents exponential functions. And the number that we multiply tells us our base or our growth factor. So b equals 3, m equals 3. And the slope for linear, the number that we're adding gives us the slope. All right, so let's go to problem number 7. This one's worked too, actually. Let's go to one that's not worked. Problem number 8, a you try example. What is the exponential function? So we're given a function here. The outputs are 3.3, 10.89, 35.937, 118.5932. Now, the last exponential table we looked at, it was really easy to tell that the outputs were being multiplied by 3 because they were all whole numbers. 1, 3, 9, 27, 81. But here we have decimals. So we're being told that this is exponential. How can we figure out what number we multiply by to get to the next number? And then how can we write out what the exponential function is? Okay, so our hint is, it says use successive ratios to determine the growth factor b, and then write the function represented, and we're going to assume that a equals 1. I want to focus on this term successive ratios. Ratios mean that we are dividing by something. We want to divide, let me just identify these as y1, y2, y3, and y4. You divide y2 by y1. And then see what you get. And then y3 divided by y2, and then y4 divided by y3. These are successive ratios. If these numbers are all the same, then boom, we found the number that we can multiply by to get us to the next output. That tells us our base B, which is our growth factor, and we can write out this function. We're definitely going to need our calculators for this. So for the first one, we have 10.89 divided by 3.3. 10.89 divided by 3.3 is 3.3. All right, for the next one, 35.937 divided by 10.89. Oh, look again, it's 3.3. And then for the last one, 118.5921 divided by 35.937. You get a longer decimal there, but it's approximately 3.3. All right, so what we see here is the successive ratios equal 3.3. This tells us that B is equal to 3.3. And we were given that A equals 1. So putting those two things together, the exponential function is going to be of the form y or f of x. It doesn't matter which one you use. Y equals, well, it said function, so let's use function notation. F of x equals a times b to the x. This would be f of x equals 1 times 3.3 to the x power. Or you can just write it as f of x equals 3.3 to the x. All right, what we just did in this example is we took a table of data, and from the table, we looked at the successive ratios, okay? We determined that the successive ratios are constant, and then we're able to say, hey, when our successive ratios are constant, we have an exponential function, and that successive ratio tells us what our B value is. For problem number 9, we're given 2 sets of data, and we have to determine whether or not the data is linear or exponential. How can we do this? Well, if it's linear, we would be adding a number to get to the next output. If it was exponential, we would be subtracting. So for the linear one, we can look at, or for both of them, we don't know which is which. We can look at the average rate of change, so the change in the outputs over the change in the input, or we could look at the successive ratios. We have to check both. If the average rate of change is constant, it's linear. If these successive ratios are constant, it's exponential. Or you might be able to just look at this and identify the pattern. Like here, I can kind of tell if I go from 1 to 5, and then from 5 to 25, and then 25 to 125, it looks like I'm multiplying by 5. And we are. So if you visually see this, you can see that this is times 5, times 5, times 5, times 5, times 5, times 5. If you recognize that, cool. We can say, oh, this is an exponential function with a base of 5. If you don't recognize that, then you should do a little bit of dividing. You'd have to be careful with this. So again, to be clear, you can stop there if you recognize that the outputs are being multiplied by 5. If you don't, then you would look at the ratios. 1 over 5 divided by 1 over 25 equals 25 over 5, which is 5, okay? Then 1 divided by 1 over 5 equals 5 over 1, which is 5. Then 5 divided by 1 is 5. 25 divided by 5 is 5. We see the pattern here. We see that the successive ratios are all equal to 5. So this tells us that it's exponential. And we need to write out an equation of the form y equals mx plus b. I'm sorry. Oh, Lord. Y equals a times b to the x, not mx plus b. All right. So what information do we know? Once we get these successive ratios, the number that we get tells us our b. So b is equal to 5. And the a value is going to be whatever the initial condition is, or the y-intercept. In this case, we have 0, 1. So from the table, we see that a is equal to 1. Okay, then putting that information together, we'll have y is equal to 1 times 5 to the x, or just 5 to the x. So this is a table of the function 5 to the x. For part B, it's not very obvious that the ratios would be constant or not here. We can check. We can do 3 divided by negative 3.2, and then negative 2.8 divided by negative 3. Let me see what these things are. 3 divided by negative 3.2, that's 0.9375. And then negative 2.8, sorry, both of these were negative. Negative 2.8 divided by negative 3. That is 0.933. So these are different. They're not equal. You can see that this is not exponential. But if we subtract the outputs and look at the rate of change, let me write it this way. To go from negative 3.2 to negative 3, we're adding 0.2. To go from negative 3 to negative 2.8, again, we're adding 0.2. The difference between those two numbers is 0.2. From negative 2.8 to negative 2.6, adding 0.2. Okay, so we see here that the outputs are increasing by 0.2. So this is linear. And the slope is 0.2, with m equal to 0.2. All right, so write out this function. We need to, or equation, we need y is equal to mx plus b. We found that m is 0.2. From the table, we see that b is equal to negative 3.2. Do not mix up the b in the exponential function with the b for a linear function. B for your linear function is the y-intercept, okay? And putting those two things together, we'd have y is equal to 0.2x minus 3.2. All right, now we know how to identify an exponential function from a table. So far, all of the problems that we've worked with have been growth problems where our base is bigger than 1. But we can also have a base being between 0 and 1. So like a base of 0.5 or 3/4, something like that. Those would give us exponential decays. Which brings us to problem 10. So use successive ratios to identify the exponential data. Given the table above, explain why the table represents an exponential function. Use the idea of successive ratios in your response. So let's look at these successive ratios. We do 12 divided by 15. That's 4 over 5, or 0.8. Okay, then if we do 9.6 divided by 12, again, that's 0.8. Then let's just check the next one to be sure. 7.68 divided by 9.6. Again, that's equal to 0.8. So we see here that the successive ratios are constant. So this is an exponential function. With b equal to 0.8. Okay. Oh, that's the answer to the second part. So part B, determine the value of b, which is called the decay factor. B is equal to 0.8, and it's, again, because it's less than 1, it's a decay factor. When b is greater than 1, we call it a growth factor. And why is there no part C here? There should be a part C. We can put this all together and write out the function. The function would be f of x equals, for our a times b to the x, a is 15, because that's the initial value from the table, or the y-intercept from the table. B is 0.8, so we get f of x is equal to 15 times, I'll use parentheses here, make it a little bit easier, 0.8 to the x power. Problem 11, I do want to do this one. How do we fill in the rest of this table? Complete the table below by using the decay factor b. We are only given 2 things in here, but we're told it's exponential and we have a decay factor. So we can look at the ratio of the outputs. Remember, it's the second divided by the first, then the third divided by the second. So we'll do 6 divided by 36. That's equal to 1/6. Okay. So b is equal to 1/6 here. How do we fill in the rest of this table? Multiply each output by 1/6. And just keep going. So 6 times 1/6 would be 1. 1 times 1/6 would be 1/6. 1/6 times 1/6 would be 1/36. 1/36 times 1/6 would be 1/2 something, 216? 6 times 6 times 6, 216. And if we multiply by 1/30, I'm sorry, 1/6 one more time, 216 doesn't look very clear. All right, and if we multiply by 6 one more time, you get 1/1296. You can write those as decimals if you want to, but you can leave them as fractions also. It's a little clearer, I think, when you write it as the fractions. All right, next, it kind of summarizes what we talked about earlier with exponential functions that were growths, but now we're adding decays to it. So for an exponential function of the form a times b to the x, when b is greater than 1, we have a growth. But when b is between 0 and 1, we have an exponential decay. All right, number 12 is a worked out problem. So we're going to skip over that and go to the next U-try. Here we're given a bunch of exponentials and a linear function. We have to determine which one has a decay or growth factor. So determine if the function has a decay or growth factor. Part A, y equals 1.03. B is equal to 1.03. That's bigger than 1. So this is a growth factor. It's increasing. For the next one, 0.8x, b equals 0.8. That's less than 1. So this is a decay factor. For G, 3/2 to the x power, or part C, g of x equals 3/2 to the x power. Our base is the fraction 3/2. This fraction is 1.5, so that's bigger than 1. This would be a growth factor. Part D, v of x equals 0.75x. It's linear, so it has no factors, not growth or decay. All right, for E, our base is 9/11. This is a fraction that's less than 1, so this would be a decay factor. And last one, 5x over 6. Don't let it stump you. Again, this one is linear. That's 5 over 6x. The exponent isn't an x, okay? So that's linear, which means that it has no factor. All right, now we know what an exponential growth is, or what it looks like, the function. We know what an exponential decay looks like. We want to think about, lastly, what the graphs of exponential functions look like. They all have a very similar shape, but exponential growths increase and exponential decay models decrease. So we'll see the difference between that. All right, for 14, we're asked to graph 2 to the x. So graph the function 2 to the x using the window -10 to 10, -2 to 10, and 1. You could do this on your calculator. And then it says use the graph to identify the y-intercept, and then write it as an ordered pair. And then from the graph and the trace feature, trace what's happening as we go to -infinity. We'll do that on Desmos. All right, so the graph of 2 to the x. Oops, that's 2 squared. 2 raised to the x power. Ta-da, here it is. So I'm just gonna start at 1, the y-intercept. The y-intercept is 0, 1. And as we go to the right, the graph increases very, very, very quickly, as we saw earlier when we kept squaring and ended up at $21 million, okay? Increases very, very, very quickly. However, this question was asking us to explore what happens as our exponent gets more and more negative, all right? So if we trace this graph to the right, we have 0.4, 0.3, 0.2, 0.1, 0.06, 0.05, 0.04. These numbers keep getting smaller and smaller and smaller. They get closer and closer to 0, but they actually never touch 0. So what we have going on here, if I zoom out, notice the graph just looks like it's blending in with the x-axis. It actually never touches the x-axis. It just gets closer and closer to it. This is called a horizontal asymptote. It's a horizontal line that our graph approaches but doesn't touch. In this case, the x-axis, or the line y equals 0, is a horizontal asymptote. Summarizing the stuff here in 14. Our graph look like this. Let me put in a couple of points that are actually on here. It will be 1, 2, 2, 4, 3, 4, 5, 6, 7, 8, 8. So the graph would look like this, increasing super fast, gets close to the x-axis but doesn't touch. The y-intercept is at 0, 1. Does the function have an x-intercept? No. The graph never actually crosses the x-intercept. What's the domain and range of the function? If we look at this graph, it'll keep going out both ways. It'll keep going all the way to -infinity for x and go all the way to +infinity for x as well. So the domain for the domain for this function is all row numbers. Or if you look at the function itself, 2 to the x, we can plug in anything for x. So the domain is all row numbers. You might see it in interval notation sometimes too, -infinity to infinity. However, for the range, if we look at this graph, the entire graph is above the x-axis. We never attain any negative y values, right? So that means that the range is going to be from 0 to infinity, but it doesn't even include 0. It will be all positive real numbers. So that would be from 0 to infinity. In summation, for exponential functions of this form, x can be anything. Your outputs that you get are going to only be positive numbers. And as I mentioned, What's happening there at the x-axis is called a horizontal asymptote. So in this case, we have a horizontal asymptote at y equals 0. The graph gets very, very close to 0, but it doesn't touch or cross it. All right. 15 is a worked example, just showing us another exponential function. Actually, I want to go to Desmos really quickly. We have 2 to the x in here graphed. What if we look at different growth functions? 5 to the x, 10 to the x. What's another one I can do? 1.5 to the x. And I'm going to zoom in here so you can see these a little better. Notice first that if we look at each of these individually, they all have the same kind of shape. They also all have the same y-intercept, 0, 1. They all have this horizontal asymptote at the x-axis, y equals 0. And they're all exponential growths, but the graphs are different. What's different? The difference is the steepness of the graph, or how fast the graph increases or grows. The bigger your base, the steeper or the faster your curve increases. So if we look at these from smallest to greatest, the smallest base is 1.5. This function is growing the slowest. When we look at 2.5 to the, 2 to the x, notice the graph grows faster. The x values go up faster than they do for the purple graph, okay? As our base gets bigger, the graph has the same shape, but the increase is just gonna be steeper and steeper. So 5 to the x and then 10 to the x. Come on, 10 to the x. If we did 20 to the x, it would be even closer. The top part would be even closer to the y-axis, a steeper graph. All right, so all exponential growths kind of have the same shape. They all have this y-intercept and they all have this horizontal asymptote. Let's summarize that. We'll talk about the difference between the graphs of exponential growths and decays. So for a growth, we have y equals a times b to the x. For all of these, a is going to be greater than 0. For exponential growth, b is greater than 1. We're going to have a graph that has this shape. Increasing, y-intercept at 0, 1, and we have a horizontal asymptote at the y-axis. So for 2 to the x, 5 to the x, 1/2 to the x, 1,000,000 to the x, it'll have this shape. The y-intercept will be at 0, 1. We have a horizontal asymptote. Now, this is very important. The horizontal asymptote is a line. It's a horizontal line. So we have to write it as the equation of a line, which is y equals 0. The domain is all real numbers. And the range is all positive numbers. This is true for any exponential growth. All right, I'm going to move that over here. For an exponential decay model, let's look really quickly at exponential decays. We need our bases to be smaller than 1 to be an exponential decay. So let's look at 1/2, 1/5, 1/10, and 1/1.5. That'll make it easy. So parentheses, 1/2 to the x power. And then we want 1/5 to the x power. And I'll just do one more, 1/10 to the x power. All right, for exponential decay functions, the reason that they're called decays is because they're decreasing or decaying. The graphs start off really big, and then as X increases, the graphs get smaller and smaller and smaller and smaller and smaller. The graph approaches the X-axis, but it doesn't actually touch across it. So we still have this horizontal asymptote. And guess what else we still have? The y-intercept is still 0, 1. The graph is still all above the X-axis. The domain is still all real numbers. The range is still all positive numbers. What's different here is that now the graph is decreasing instead of increasing, okay? Also, I wanna just point out one more thing and we'll go back to our book. Let's compare the graphs of 2 to the x to 1 over x, to 2 to the x to 1/2 to the x, I'm sorry. They're inverses of each other, okay? One is a growth, one is a decay. The rate at which 2 to the x is growing is equivalent to the rate at which 1/2 to the x is decaying, okay? So for exponential decays, we still have y equals a times b to the x, but this time b is between 0 and 1. The graph will be a reflection of the growth graph. So we start off really big, and then we decrease and get close to the x-axis. We still cross the x-axis at 0, 1. And it turns out that all of this information that I wrote here, the y-intercept being 0, 1, horizontal asymptote y equals 0, domain and range, that's the same for growth or decay. All right. I always like to summarize that. All right, we're just gonna take a couple more minutes to definitely do problem 17, and then I think I wanted to do problem 15 is already worked out for us. We can do problem 16 too. This is a word problem. After a snake bite, a man was given an anti-venom injection to counteract the venom in his bloodstream. Let's assume that after every hour, the quantity of venom in his bloodstream reduces by half. Okay, so he starts off, he got bit, has a lot of venom in here, took some medicine, so the amount of venom is decreasing, it says, by half every hour. Okay, so use this information to complete the table below. This input 0, 1, 2, 3, 4, 5, and 6, that tells us the time after the anti-venom has been given to this person or injected. So in the time in hours. And then the output is how much venom is left in his bloodstream. So if he starts off with 1 milliliter of venom, we have half of that after an hour. So then he'll have half of a milliliter. And then after another hour, if we divide by 2 again, half this, so multiply by 1/2, we'll have 1/4 of a milliliter. And we keep multiplying by 1/2. It'll give us 1/8, then 1/16, then 1/32, and 1/64. Okay. What is the common multiplicative step for the Q of T values? To get half of something, you multiply it by 1/2. Okay. So we multiply by 1/2. That tells us what our base is for our exponential function. So write Q of T, an equation that tells us the amount of venom in this person's bloodstream. We start out with 1 milliliter, so A is 1. From the last part B, we see that B is equal to 1/2, and then the function Q of T would just be 1 times 1/2 to the T power. Or you can just write this. We usually don't write the 1, so we'll write it as 1/2 to the T power, not the X power, or not the second power. All right, when we graph this, we just graphed it actually, the reflection of 2 to the X. The graph will be here. 1/2 to the first power is 1/4. And then we have 1/8, and then 1/16. We'll get these points that are getting really, really, really close to the X-axis. But then if we go the other way, we have 2, I went too far, 4, 8, boom. The graph is really, really big. And then as x increases, the function decreases. So is this a growth or a decay? It's a decay. And then what's the y-intercept? We see from the graph and from the table that the y-intercept is 0, 1. There is no x-intercept. The horizontal asymptote is at y equals 0. And for the range, again, y values can never be negative. So the range is 0, infinity. All right, very last thing here. We want to take some exponential functions, identify the base, state whether it's a growth or decay factor, find the x-intercepts, the y-intercepts, and the horizontal asymptotes. All right, for all of these, our a term is 1. When a is equal to 1, well, I should actually fix that. For these, the way that I drew this down here, a equals 1. So I'll add that here, a equals 1. All right, when a is equal to 1, your y-intercept is going to be 1. We already showed from our graphs below that the horizontal asymptote is always 1/2. I'm sorry, the horizontal asymptote is always 0, y equals 0. And none of these functions are, these exponential functions are going to have x-intercepts. So we can kind of fill in this stuff. The x-intercepts are going to be none for all of these. The y-intercepts are going to be 0, 1 for all of these. And again, that's because we have a is equal to 1. If a is equal to something else, then 0, that number. 0a will be your y-intercept. And the horizontal asymptote is the line y equals 0. This is the x-axis. All right, now the rest of this stuff we need to find. For 2.03 to the t, the base is 2.03, and that would be a growth. I'm just going to put G for growth. For 3/2 to the x, the base is 3/2. That's bigger than 1, so that would be a growth. For h of x equals 3/5 to the x, the base is 3/5. That's less than 1, so this would be a decay. And for g of t equals 0.83 to the t, the base is 0.83, which is less than 1, so this is a decay.